Well, for Theorem 5.9, let's remind ourselves what an altitude is. Extending from a vertex to the opposite base, like that. Or from this vertex to its opposite base, like that. Or from this vertex to its opposite base, and be like that. Every triangle, 3 bases, 3 altitudes. So they also have a concurrency point called the orthocenter, and we're calling that G right here. And as we remember, an altitude might be inside the figure. It could actually be on the figure. How about a right triangle? Look at that. 2 of the legs of a right triangle are altitudes. Therefore, the orthocenter is a vertex. The orthocenter is on the inside. The orthocenter is on with a right triangle. And then when we go obtuse, the orthocenter is outside the triangle. Well, let's consider the segment BD with respect to the triangle ABC. Let's see, is it a perpendicular bisector? Well, let me see, it's perpendicular and it bisects right there, bisecting AC. So I'd say that gets a solid yes. How about a median? Drawn from a vertex to the midpoint of the opposite side. Very definition of a median. So that's 2 for 2. Let's go for the trifecta. Altitude. It's drawn from a vertex perpendicular to the opposite side. So 3 yeses. Well, here we go. Exercises 18, 20, and 22 in your textbook. You were given one diagram. I've repeated it 3 times with the 1, 2, 3 different cases of givens. Let's take 18 first. I've got a pair of congruent angles. And I look at those and say, well, yeah, that's obviously by definition, that's going to be an angle bisector. But what about everything else? Perpendicular bisector, median, altitude. All I've got to do is tug on this. Let me do that again. All I've got to do is this. Aha. And I can show you no. All you've got there is an angle bisector. I don't have any information, nothing to say perpendicular, nothing bisecting, and nothing about altitude. So, angle bisector, that's all you've got. That was easy. Let's go to 20. Well, let me see. It's a perpendicular bisector right off the bat because it's right here. We want this perpendicular, and we're bisecting XZ. Well, that's all right. Let's look for the other. Let's look for something less obvious. 2 triangles congruent by side angle side. I'm of course using this side. And then by corresponding parts of congruent triangles, these 2 angles are congruent. That makes this XW or WY an angle bisector. Okay, so we've got 2 out of 4. Let's keep going. Well, I'm drawing from a vertex to the midpoint of the opposite side. That's the definition of a median. And when I draw from a vertex perpendicular to the opposite side, that is an altitude. 4 for 4 on number 20. Way to go. All right, 22. I've got these givens here. You know, same thing. HL. I've got 2 congruent triangles by HL now. When I do corresponding parts of congruent triangles, put my little CPCTC over there, I'll make these angles congruent and also these sides. And right away, that's going to give me the perpendicular bisector. I see perpendicular, I see bisect. That's going to give me angle bisector. I've got 2 congruent angles. And let me see, the median, vertex to the midpoint of the opposite side. That's a median. And from a vertex perpendicular to the opposite side, that is an altitude. Whoa, another one, 4 for 4. Well, we've got an isosceles triangle here, and if we throw in this little right angle, that makes BD an altitude. As we've discussed, the altitude of an isosceles triangle is both a perpendicular bisector and an angle bisector. We've done the proofs already, so there it is. So of course, this side would be 6 to match AD, and I've got a pair of 22-degree angles. Almost the same diagram, except now we're given these two. Segments are congruent or have equal measure. And now this is a case for the converse of the perpendicular bisector theorem. Because after all, this point B is equidistant from A and C. So it's on the perpendicular bisector of AC. Now D is also equidistant from A and C. So it is also on the perpendicular bisector of A and C. So I could conclude that this is the perpendicular bisector. Now there's actually some theorems in other textbooks that say 2 points equidistant from the endpoint of a segment determine the perpendicular bisector of a segment. I like that too, but we could piece it together the way we did. And now you've got this. If it's a perpendicular bisector, then of course perpendicular here, and that makes it an angle bisector because it's altitude, after all, of this isosceles triangle. Well, let's place an isosceles triangle on a coordinate plane. It's got a base of 2n and a height of h. Well, let's do the most obvious. We'll start out right here. That's probably what you were expecting. I've got triangle ABC here. Clearly AB, see, it straddles the y-axis over here, so I've got a distance from negative n to positive n, a base of 2n. That's probably the most likely. But, you know, you could shift the whole thing over to the first quadrant, and then you've got this. So, again, there's nothing wrong with it. Notice now that the coordinates of F are NH and E2 are 2n, 0. But let's not stop there. Who says the base has to be on the x-axis? How about this? Let's put it on the y-axis. If you will, just the blue one rotated 90 degrees clockwise. And finally, how about a green one? Same thing there. Just placing it in the first quadrant, but again using the y-axis for the base. All of these are possible arrangements for an isosceles triangle on the coordinate plane. Well, this proof looks like so much fun, we're going to do it twice. This is the A version for 42. We're going to use congruent triangles to prove that BD is also a perpendicular bisector, since it's an altitude of this equilateral triangle. Pretty straightforward. All right, I can just say angles 1 and 2 are right angles. Let me see, I guess I'm going to have to put in a 1 and a 2 then. There you go. And that's a definition. An altitude is drawn perpendicular to the base. About number 3. Good old friend, the reflexive property. BD is congruent to itself. And I've got 2 triangles. I've got this one and its reflection, congruent by hypotenuse leg. And, well, I guess you see where it's coming next. By corresponding parts of congruent triangles, I've got the segment AD congruent to DC. Now, if I've got a segment that's perpendicular and bisects a segment, I guess, by definition, it is the perpendicular bisector of the segment. Well, let's try that same proof a different way. Same givens, ABC is equilateral, BD is an altitude. So let's, how about this? Well, B must be on the perpendicular bisector of AC. And that's very simply put. Theorem 5.3, converse of the perpendicular bisector theorem, states that if a point is equidistant from the endpoints of a segment, as indicated here, it's equidistant from A and C, therefore it is on the perpendicular bisector of AC. Enough said. Let's try something else. Oh yeah, and there's that little matter of this altitude business, and since since BD is an altitude, by definition, BD is perpendicular to AC. And then we go way back, early chapter, postulate 14. Well, postulate 14 says if we have a point, well, we have a line, or a segment in this case, and a point not on the line, there's only one line perpendicular to that line passing through this given point. And since there's only one line perpendicular and it passes through this point, and BD is on the perpendicular bisector, as we said in 2, therefore BD must be the perpendicular bisector of AC. Pretty clever and an elegant solution where we didn't have to use congruent triangles.